hope so. Okay, so first let me revise very briefly what I've said yesterday. So we want to study finite dimensional algebras over an algebraically closed field, okay? And basically what I said yesterday is that this basically means studying representations of quivers bounded by an admissible ideal I. So for any finite dimensional algebra, we can find a quiver with an admissible ideal for which the module category is the same as the module category of the bound path algebra, and that is the same as looking at representations of quivers, which is assigning vector spaces to vertices and linear maps to arrows and morphisms between them. So it's a more hands-on approach to this slightly, I suppose, more abstract category, which is the module category of A. Okay, so, but now we actually want to understand the module category, so we want to understand these representations. And for this, we're going to use a very, very powerful theory called Alexander-Reiten theory. And this was created by Alexander-Reiten in the 70s. And so this is going to give a very powerful way of studying the representation theory of an algebra, because ultimately we're actually going to be able to see not all of it, so sometimes all of it, sometimes not all of it, but part of, at least, of the representations of a quiver bounded by an ideal I, by using a quiver. Again, we associate a quiver to this category. This is called the Alexander-Reiten quiver. And when, for example, so also mentioned yesterday, Gabriel's theorem, which classifies representation finite hereditary algebras. So when the algebra is a path algebra of a cyclic quiver, then so these have a finite number of incomposable modules, and this quiver will give a complete picture of the module category for those algebras. And hopefully, with what I'm gonna explain today, this theory, we're gonna be able to construct those quivers. We're gonna be able to create a complete picture for this category. So that's the aim. But okay, so this is quite an involved theory, so there's going to be lots of definitions and results that I'm going to throw at you today. But hopefully at the end we're going to be able to compute things, so it's going to be quite computational in the end. Okay, so I don't know your background, so I'm going to assume this is not known, but if it's known, you just revise it. So we take a sequence of morphisms in the module category, like this. We'll say that this is exact if the image of a morphism is the same as the kernel of the next one. Okay, so in particular, the image of Fi is contained in the kernel, meaning that the composition of two arrows in this sequence is 0. So we're always going to have that. And then if you have a special form, if you have an exact sequence of this form with 3 objects here, zeros at the end, then this is called the short exact sequence, and I'm going to abbreviate from now on with SES. So by this definition, this means that that this thing here is injective. This is because of this. This map here, the end, is surjective, and the image of F equals the kernel of G. I'm also going to say that this exact sequence of this form is an extension of the last term, M, by the first term, N. Okay, so for example, so if you have two modules, M and L and N, then you can, for example, just consider the direct sum in the middle term, and you just include, this is the inclusion of L here, and this is a projection, and then you can easily see that this is a short exact sequence. It's not a very interesting short exact sequence. We're going to give a name to this, but we can also associate a exact sequence from a morphism. So if you have this, then we can consider the kernel included in M. Then, for example, have this, and consider the co-kernel of F. And this is the projection. Then this is exact sequence. Okay. Right. So now I'm going to define a special, well, what I said before, a not very interesting short exact sequence. For this, I need these definitions. So a morphism F from M to N is a split mono. And you can also see in the literature with section, but I prefer this expression because it already says that it is a monomorphism, for example. If there is a map in the other direction, such that GF equals the identity of M. So there is a left inverse. So F is a split mono if it has a left inverse, and F is a split epi, or also called retraction, if it has a right inverse. Okay, and I'll say that two extensions of M by N, so two exact sequences of this form, are equivalent if and only if the middle terms are isomorphic and this isomorphism gives commutative diagrams here. Okay, so this is what I call equivalent extensions. So, well, it's an exercise to check this. So if you have a short exact sequence, then F, the first map F is a split mono, if and only if G is a split epi. And this is the same as saying that this sequence is equivalent to this sequence that I said. It's not very interesting. So the middle term is always the direct sum of the outer terms. And this is inclusion of projection. So they're equivalent. And in this case, a short exact sequence of this form, we say that is split. Right, so the middle term is the sum of the outer terms. Okay, for this, so this is something that is going to be, well, this is an important space, and this is a set of equivalence classes of extensions of M by N. And we say that this is well, we can be checked, then we can define a sum here, and this is as the structure of an abelian group. And the zero element is this split extension, so this split short exact sequences. Okay. Right, so let me give you examples with the representation theory of quivers. So yes, so let's say this quiver. Then, so the zero representation is just zeros on both vertices. Then we can consider this representation, say. The maps are obviously zero. And this, so the first map is the identity, the other zero. Then, sorry. This and then this. Okay, so we have these representations. We have morphisms between them, so this is obviously zero. If we put this here, then you can check, so these are actually morphisms, and you can check that this sequence, so this is zero, this is L, This is M, this is N. This is a shortest X sequence. You could do the same as here. But now actually you swap these maps. Identity here, 0, 0, 0. Then here, so this is again L, this is M prime, this is N. This is another shortest X sequence. So these are shortest X sequences. But they are not equivalent. You can actually check that there's no maps between M and M prime, non-zero maps, so they can't be isomorphic. Okay. Right, so this is one ingredient, shortest X sequences. I'm gonna expand more on this. I'm gonna actually study a special case of exact sequences. But first of all, before that, I'm gonna concentrate on special types of representations in the composable, in the composable one. So simple, projectives, and injectives. And this is going to be quite useful to construct the on the right quiver. So just, I don't know if you study this, but just so you know what this means. So as a module is simple if it is a non-zero module that has no proper submodules. Okay, and then a module is projective if any shortest X sequence ending at P splits. And the injective is kind of the dual, so any shortest X sequence starting at I splits. You probably saw this definition instead, but this is the same. So if you have a projective module and you have an epimorphism, which I denote by this, any map from P to the n term factors through the first one. Okay, there's something like this, and then the same with a dual with injectives. Now, if you have a monomorphism and a map from the first term to the injective, then this map factors through this monomorphism. Okay, so, but this is the same as saying that this shortest X sequence is an NP splits. And this is actually some property to keep in mind when I define the exact sequences later. Right, so why do I say this? It's actually quite easy to compute the representations associated to simples and incomposable projectives and incomposable injectives. And I'll describe this, so this can be proved, but I'll just give the description. So now, as I said, because of the lecture before, I'll just consider bound path algebras. So Q is finite connected and I is an admissible ideal. So in this case, simple A modules, the representation corresponding to simples are of the following form. So there's a simple for each vertex of the quiver, which we'll denote by Si. And so this is a collection of vector spaces, what they're going to be. So it's going to be a copy of the field K in a vertex corresponding to the simple, so Sii, and 0 elsewhere. If it's 0 elsewhere, there's not much hope, there's nothing else to define here. So the maps must be 0, right? Okay, so this is, as the name says, they are very simple. Projectives. So now projectives, what you're going to do, again, projectives and injectives. There is an incomposable projective for each vertex of the quiver. And what they're going to be, so the vector space at vertex J, this will be generated, so this vector space generated by paths, okay, which start at the vertex I, so P, the projective at I. So you're looking at paths starting at I and ending at the vertices. So at vertex J, Pij is generated by the paths from I to J. The injectives are dual, so you look at paths ending at the vertex corresponding to I. So Iij is generated by the paths from J to I. Okay, so what are the maps? So the linear maps, so linear map var phi, alpha, sorry. So this starts at Pi at the start of alpha and ends at Pit of alpha. So here you have paths from I to start of alpha, and you want to map it to here. So you just compose that path with alpha on the right? So you concatenate. And so this defines the map. The other way around, we'll see this in an example, but basically you just delete the arrow alpha if you start with something that starts with alpha. Okay. So example. Let me see. So 1, 2, 3, 4. And here I don't want any so I is 0, is the admissible ideal is just 0. And this is a cyclic, so it's okay. So alpha, beta, gamma, delta. No. Okay, so this is the quiver. So what's the projective 1? So at vertex 1 is just the path that started and ended 1. This is just a constant path here. So we put a copy of k because it's just generated by one path. And then at 2 we have alpha and beta gamma. So we have 2 paths, so k2 here. For 4 there's just one path, beta. So this is k. And for 3 we have alpha delta, beta gamma delta. So 2 again, k2. Okay. So I'll put here the basis. So this is gamma, alpha, beta gamma, beta, alpha delta, beta gamma delta. Okay, so we have this. So what are the maps? So this linear map here corresponds to alpha, so we just concatenate alpha on the right. So you get the constant path epsilon 1 maps to alpha, right? So we get 1, 0. Here it's beta, so you just concatenate, you just get 1, so it's 1 here. This beta here will map to beta gamma on this map, so 0, 1. And here you get 1, 1, 0, 0. So alpha maps to alpha delta, and beta gamma maps to beta gamma delta. Okay, so this is what the projective is. 1. Let's do an injective. So let's do injective at 2. So at 2, it's the paths starting and ending at 2. So this is just the constant path k. So here you have k as well. There's only one map, and here k squared. And there's no maps from 3 to 2. So here 0. Okay, so let me put this is gamma, alpha, beta gamma, and this is just epsilon 2. So here what you do for the linear maps is you delete that map, the arrow corresponding to that map. So here you have alpha here. So from here to here you delete alpha. So you map alpha to epsilon 2. But here, if you can't, if this error here this path here doesn't start at that arrow, so it just maps to 0. So here is 1, 0, and then here's 0, 1, 1, and this is obviously 0. Okay. Let's say S3. S3 is very simple, so it's just 0, 0, K, and K, and then 0 here, sorry. So 3 is actually a sink. This means that all the arrows arrows incident at 3 have 3 as a target. So 3 is just the target of arrows. And this means that the projective at 3 is just the simple at 3, right? There's no paths starting at 3, so except for the constant one here. So this is the same as P3. So P3 is a simple if and only if Pi is a simple if and only if I is a sink. And then you have the dual, which is say S1 equals the injective at 1. Okay. A nice thing to observe and to have in mind is that so if you have any representation, you can actually see if it has maps from projectives or if it has maps to injectives by looking at this at the vector space and the corresponding projective. So Mi, the vector space Mi is isomorphic to this Ohm space from Pi to M, and is also isomorphic to Ohm space from M to Ei, to the injective at I. So this is quite nice and useful. I'm going to also need to define this. So a dimension vector of a representation, which I'll denote by this, it's just a collection of dimension vectors of the vector spaces at each vertex. So remember, we're talking about finite dimensional algebra, so modules. So we have this, and so we can deduce that if we have a short stack sequence, then the dimension vector of the middle term is the sum of the dimension vectors of the outer terms. And this is going to be quite useful to construct these also on the right hand quivers, especially for this hereditary representation of finite algebras. So keep that in mind. Okay, so the next step. So I'll define a few. I told you how to describe some special in the composable representations, the simples, projectives, and injectives. This is going to be useful. Another thing that is going to be useful is this irreducible morphisms and what I said before, this special class of short stack sequences, which we'll call also on the right hand sequences. So this is what we're going to define now. So what is irreducible morphism? So we have a morphism. It's reducible if it's not split mono, so it doesn't admit a left inverse. It's not split epi, doesn't admit a right. It does not admit a right inverse. But if you factorize f like this, if f equals gh, then this guy here is a split mono, or this guy is a split epi. So you don't have many interesting factorizations of f. So in some sense, this will be the building blocks of morphisms. So in the same way that in the composables, modules are the building blocks of all the modules, we're gonna consider this to be the building blocks of morphisms. Right, some properties of these which will be useful to know is that, so if you have a reducible morphism, then it must be either injective or surjective, but it cannot be both. Of course, if you were injective and surjective, be a bijective, and then you would admit the right and left inverse, so it wouldn't be irreducible. Okay, but let me just give a quick proof. So let f be irreducible, and suppose f is not surjective. Okay, so we're going to create the factorization of F by considering these maps. Okay, so just have this, and then the inclusion of the image of F into Y. Okay, note that because F is not surjective, this implies that its inclusion is not a split. No split epi. Sorry. Okay, so we have F equals this composition, and because F is irreducible and this is not split epi, then F bar is split mono, so it's injective. The composition of two injective, so F is injective. Okay, this proves the first statement. This is the second statement we can prove similarly. And it says that a morphism is irreducible if and only if it admits non-trivial factorization. So really, as I said, they are the simplest somehow morphisms. They will be the building blocks of the morphisms. Okay, example. So let's say we have S3. Now we know what this is. And we have P1. Now we know what this is this representation. You can see that there's a morphism here. This diagram commutes to its representation, but it is not irreducible. Because you can actually factorize this through P2. So you have P2 in the middle here. Just put ones where you can and zeros elsewhere. Then this is the same map as the above. Okay, so it's not non-trivial factorization, so it's not reducible. These two maps here are irreducible. Right, okay. So now, ozone Writing sequences. So what is an ozone Writing sequence? Again, it's going to be the simplest possible, but the simplest interesting possible one. So the non-interesting ones are the split ones. We don't want this to be split. So we said that this is an ozone Writing sequence, also known as almost split exact sequence, if the first map here is left almost split. What this means that F is not split mono. So again, so it's not split. Okay, the sequence. F is not split mono. But if you have another non-split mono U here, then this factors through F. Okay. We need this assumption here because if this was split mono, and if this was true, this factorization, then we could actually find a left inverse for F, and so F wouldn't be, then F will be a split mono, right? Okay, so we want that to happen, and also want F to be left minimal, meaning that if we have an endomorphism of M such that HF equals F, then H is an automorphism. Okay. So we want these properties for F, and we want some dual property for G. So we want G to be right almost split if G is not split epi, and any non-split epi factors through G here, adding in it. And G right minimal if G H equals G implies H is an automorphism. I could actually define this using already the previous terminology. So it can be proved that a short exact sequence is an ozone Writing sequence if and only if the outer terms are indecomposable and the morphisms F and G are irreducible. Okay. So as I said, an also on the right-hand sequence is never split, because the first map cannot be a split mono, and the second map can't be a split epi. So they never split. What does this mean? This means that we cannot have an also on the right-hand sequence starting at an injective, and we cannot have an also on the right-hand sequence ending at a projective. Okay. Another nice property is that an also on the right-hand sequence is uniquely determined by each of its end terms. So let's see this quickly. So let's suppose f and f prime, which start at the same. So we're going to see that if we have an also on the right-hand sequence starting at the same object is uniquely determined. So suppose we have two maps like this, and they are left minimal almost split. So this means left almost split and left minimal. Okay, so we can look at this. So f prime is left almost split, so it's not a split mono. Okay, and f is left minimal. Left almost split. So this means that there is a factorization here. So there's h here. Okay, and we can do the same here with f prime, and there's an h prime here, such that these two diagrams commute. So meaning f equals h prime h. So we can deduce that this holds, and that f prime equals h prime f prime. But again, now we use the left minimal property, meaning that this h is an auto, and this h prime is an automorphism. And so we can conclude that h is an isomorphism. Okay, so if you have two also on the right-hand sequences starting at L, we've seen that there is an isomorphism here making this commute, and you can extend this to an isomorphism here. So there is this two also on the right, the also on the right-hand sequence is uniquely determined by the starting point, but you can prove the same for the end point. Okay, so we've seen that an also on the right-hand sequence cannot start at an injective, it cannot end at the projective, but they are uniquely determined when they exist, right, by the start point or the end point. Right, so example. So we've seen before, we looked at this map here, the first map here. We've seen that this is not irreducible. So this is not on the right-hand sequence, because f is not irreducible. But you can have you can see that this is an also on the right-hand sequence. Okay. We'll see more of this when we actually build the also on the right-hand quiver of some of the quivers. So this is the power. So a priori, it's quite difficult to check something is also on the right-hand sequence, or if something is irreducible. But this theory really gives you the results actually gives you a way to compute them quite easily in quite a few cases. Right, but we need to build this construction. So this is basically, we can say that this is the main result in also on the right-hand theory, which is about the existence of also on the right-hand sequences. So if you start at an incomposable module, We know that an also-on-the-right-hand sequence cannot end at a projective, but if M is not projective, then there is an also-on-the-right-hand sequence ending at M. And again, we said that this is uniquely determined, so we'll denote this starting point by tau M. This will be the also-on-the-right-hand translate of M. You could actually properly define this in order to compute it, but hopefully maybe in the lecture 3 I'll tell you how to do it. Okay, so also-on-the-right translate. And then we have the dual. So if it's not injective, so if it's injective, it cannot start. There's no also-on-the-right sequence starting at injective. But if it's not injective, there is. And it's unique, as we've seen. And so this n term is the inverse of the also-on-the-right translate of M. And we can say, so if M is projective, tau M can say it's 0, and M is injective, then the inverse tau is 0. And we a key tool for the proof of this is something called also-on-the-right-hand formulas, which we should know if we want to know about also-on-the-right-hand theory. This is it's used several times. So this gives a way to compute extensions using morphisms and this also-on-the-right-hand translate. So if you have M and then 2 modules, then the extension of Mn is the same as the ohms. I put this bar here, means that you're factoring out, you're ignoring morphisms, factoring through projectives. And this is factoring through injectives, okay? Don't worry about this, this is just a K duality, that's fine. So basically we have this, and actually if A is hereditary, then you can actually ignore this factoring through. It's just the morphisms. Okay, this is just something to keep in mind as well. So now I can actually give the definition of also-on-the-right-hand quiver. So for finite dimensional K algebra, what will be this quiver? So it's a new quiver. It's got vertices and arrows. So the vertices will correspond to the indecomposable modules. And as I said, the arrows will be the building blocks of the morphisms, which will be the irreducible morphisms. So this has a nice property, which is, so it's a translation quiver. So we're going to have some mesh, what we call meshes, and this will encode the also-on-the-right-hand sequences in it. So if you have an also-on-the-right-hand sequences here, so the middle term doesn't have to be indecomposable, but the outer terms are. So there is a vertex for tau M and a vertex for M. So this morphism here is this. It's going to be decomposed like this, and each one of this is irreducible, and there is an irreducible morphism here from EI to M, if and only if there is an irreducible morphism from tau M to EI, if M is not projective, right? So actually, so this is how we're going to denote in the quiver. This is how we're going to draw also-on-the-right-hand sequence. But this is a bit misleading. So you could have more errors here, but it's always the same number. If there's 3 here, there's 3 here as well. Okay, and this is just the dimension of the space of irreducible morphisms from tau M to E1. And this is actually the same as the multiplicity of E1 in the middle term of also-on-the-right-hand sequence. This is why they're so important, these sequences. They really tell you how to build this picture for the category. Let me say a few more things about this. Okay, so it's a translation quiver. Maybe I'll add one. So the also-on-the-right-hand quiver has no loops. Okay, so what would be a loop? A loop would be you'd give an incomposable module M and then a reducible morphism here. But we've seen that irreducible morphisms are either injective or surjective. But then M is a finite dimensional, so this would imply that F is a bijection. But we've seen as well that a reducible morphism can't be a bijection. So contradiction. So he has no loops, and it's what we called locally finite. So this means that each vertex has finitely many neighbors. So vertices for which there is arrows pointing to it or starting at it. Why is this? So let's take a vertex which will correspond to a projective. Then it is a fact, and I'm gonna write it down later on, that any vertex for which there is a map from that vertex to P, so all the predecessors of a projective are summands of the radical of the projective. So there's only finitely many of those. What if the vertex is if it's not projective? Well, if it's not projective, then there is also on the right-hand sequence like this, and it is a fact that all the arrows pointing at with ending at M in yours on the right-hand quiver are these arrows here coming from starting at middle terms of the starting at the summands of the middle term of the also on the right-hand sequence. So it's also finitely many of those. Okay, and the same argument goes for injective. Okay, so it's locally finite and it has no loops. These two nice properties. So this is, I said before, I just said it, but maybe to keep in mind, it's nice to see written. So what is a radical? Just to remind you, a module, let M be a module. The radical is the intersection of all maximal submodules of M. And it's easy to, so as we said, if we want to look at the irreducibles ending at projectives, we have to look at the radical to check the start of that irreducible morphism. And it's actually quite easy to compute radicals, especially of these projectives. So if we have the radical of a projective is a representation, where basically is the same as a projective, but you ignore the constant path at the vertex corresponding to the projective. So QIJ is Pij if J is not I, and if for QI you look at all the paths starting all the paths from I to I which are not constant. Okay, and then the linear maps is just restricted to this submodule. Okay, so as I said, if Pi is an incomposable projective and J and X is an incomposable module, and there is a reducible from X to Pi, then X is a direct summand of this radical. This is a good starting point for our construction of the ozone quiver, and especially, so we're going to compute this for the hereditary finite dimensional finite representation type. So there, it's a quiver and a cyclic. So there will always be a simple sink, meaning there will always be a simple projective, and it's not injective. Otherwise, you'll be a source as well, but then there will be no arrows. Okay, so in that case, all the morphisms, there's no morphism. There's not going to be the radical is 0, so there's not going to be irreducibles pointing at ending at S, but all the irreducibles starting at S will be from S to a projective. Okay, so S will be the radical of that, or part of the radical of that projective. These are good starting points, and I don't have time, but I'm going to start the next lecture to describe an algorithm. So actually, I gave you all the tools so that we can now knit. It's an algorithm called knitting algorithm, and so with all these properties and these ways of computing morphisms, we can actually build and actually give the complete picture for the representation theory of hereditary algebras of finite type. Also, we can extend this, and we're going to consider other examples, but this will be the aim for the next lecture. And I'll finish here. Thank you for listening.